So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by Bill McKinnon. Bill has come across from Missouri. He's a professor at Washington University at St. Louis. He's actually come to the SETI Institute for an Enceladus workshop that has been on the last couple of days. So perhaps he's going to talk to us a little bit about the results that came up during that workshop. Bill is a planetary scientist who's interested in the outer solar system, geology and geophysics. He's worked on Voyager, Galileo and Cassini data, and he's particularly interested in topics such as large impacts, orbital dynamics, stress and strain in ice, and convection, tectonics in the icy lithospheres of the outer planet satellites. And today he's going to talk to us about the similarities and dissimilarities between two of Saturn's satellites, Mimas and Enceladus. So if you'll join me in welcoming Bill.
All right, thank you everyone. Just like Adrian said, we had a workshop the last couple of days. So even though my talk title may sound very specific, I'll spend quite a great deal of time talking about the general background about what makes Enceladus and its companion moon Mimas so fascinating. And I hope to improve upon the picture that you see here of the inside of Enceladus. Okay. What could be more beautiful than the globe of Saturn and its great moons traveling across it? You see Saturn here, its rings. There's the big giant moon Titan. I'm not going to talk about these guys at all. I'm going to talk about these little tiny white dots. In fact, these two satellites. I'm going to spin a tale about Mimas, or Mimas over here, and Enceladus, two of the smaller inner moons of the giant planet Saturn. And indeed, even though they're right next to each other in their orbits, they're almost the same size and almost the same density, but they're so different. And you might say, well, why bother with little things? Well, you know, size sometimes doesn't really matter a whole lot. You know, sometimes one nation can influence an entire globe. This satellite, which is Enceladus, influences a great deal of the Saturn system. Here's sort of like the general context, Saturn and its rings, and the innermost of the small moons. Titan is a sort of arrow out there in the coffee room. We want to talk about Mimas and Enceladus. Enceladus's influence, its empire, is this whole region from the main rings of Saturn out beyond the moon Rhea, and its influence is controlled by the appropriately named E ring, although that's not why it was ultimately named E when it was first discovered. Now, we've known Enceladus will be interesting for some years. When Voyager got there now 30 years ago, Voyager 2 in this particular image, it returned pictures like this. And for those of you who are familiar with planetary bodies, you'll recognize impact craters, which is not so surprising. The moon is covered with craters and so forth. But what made this body interesting, for its size, which is only 500 kilometers across, just like on the picture with Great Britain to scale, is that a lot of this stuff doesn't have craters. This is clearly a moon that has undergone a profound geological evolution. But Voyager, in those days, could not actually tell us what was really going on. We also knew that it was an incredibly reflective body, almost like pure white snow, the most reflective body in the solar system. Well, we sent a new machine there. It's still there, not to Enceladus specifically, but to the Saturn system, and it's been in orbit now for some number of years and returning much higher quality data. Instead of TV images, we have CCD images. Here's a typical picture of one part of Enceladus, and again, you see more craters, and I love craters, but not everybody does. Let's face it, they're a little bit boring. But that's not really what excited people about Enceladus. It's what Cassini was able to see with its fine camera. This is what it saw, and many of you already know this. If you get an image of Cassini, an image of Enceladus and process it appropriately, you in fact see that it is spewing vapor and particles out into space. Actually, you see the particles. Okay. Enceladus is geologically active. It's an icy world, And so it's, in a sense, cryovolcanically active. It has cold volcanism. This is a fascinating process to study, and one which Cassini is superbly outfitted to take advantage of. Just like there are no bad cats, there are no bad icy satellites, but in particular, Enceladus is a truly fine satellite, and Cassini has done wonders there. We, of course, have wonderful high-resolution images. Of course, we always have this for everywhere we go. We have near-infrared spectra to determine surface composition. We usually have this. But because Enceladus is active, we can use the other instruments on Cassini to learn even more, to interrogate this satellite. It turns out that we can measure the heat coming out of the active areas of Enceladus with a thermal mapping instrument. We can do stellar occultations of those plumes that you just saw and determine what the composition of the gas is. Not only that, we go by the satellite again and again and again, depending on the orbital tour. You can actually fly right through this stuff because it's just that thin. It's not dangerous. It's not like flying near Iceland right now, okay? You can measure the composition of the gas. You can measure the composition of the particles. There are different instruments that will measure gas and particle composition, and that'll all play a role. So we have this wonderful multiple data set to do geology and geophysics of an active icy satellite. These are the big clues to how all of the icy satellites in the solar system have operated. Well, here's a blown-up picture of another one. This is now what we call forward scattering, where the sun is behind you, and so it's like smoke at a rock concert. You see all these fine particles spewing out into space. Remember, this is a small body. It's only 500 kilometers across. Its gravity is only 1/100th that of the Earth. So without an atmosphere and with very low gravity, if you have any kind of geysering, which is really what these are, in a sense, this stuff will just flow out into space. It's fabulous. And it turns out that all of the activity is restricted to a zone around the precise south pole of this little moon. Let's back out. So it looks sort of gray and fuzzy here, but in fact, it really is gray and fuzzy because all this stuff is polluting the whole orbital space around Saturn. This is the origin of that thing I called the E ring. Let's back out again. Okay, again, another Cassini image. Sort of overexposed, but it brings out the details. All of these fine particles, and they really are fine. They're on the order of a micron or two, okay? Okay, they're like smoke. They're like toner powder, you know, in a copier or laser printer. Here's another great surprise. When you look at Enceladus with infrared eyes, heat-seeking eyes, so you're, you actually see that there's a hot spot right at the South Pole. Now, of course, hot is a relative term on Enceladus. You're far away from the sun. The surface of the satellite is, in fact, very cold. This is an absolute temperature Kelvin, so very, very chilly. But what the Cassini composite infrared spectrometer saw was, in fact, that there was a hot zone. Okay, it's basically the signature of volcanism, but icy volcanism. So we're talking maybe on average up to around 90 Kelvin. That doesn't sound maybe fabulous to you, but it means that there's a lot of heat pouring out of this little moon. And when we took high-resolution images, which we didn't have of this part from Voyager, we saw, in fact, that the region around the South Pole was highly deformed in this very characteristic. It's almost like someone had taken a giant Zen rake and scraped it across the surface. And you see these these are large fractures, actually. And in this image, it's a mosaic put together by Cassini. You see some of those craters that I talked about before, but lots of deformed terrain. And the zone around the South Pole is very interesting. This is an image that it uses one infrared filter in its color balance, and so it's sensitive to the particle size of the ice particles on the surface. And so this bluing here tells you that there's somewhat larger particles there. This wouldn't exactly look the way it would to a human eye, but to the Cassini eye, that's what it looks like. And when we take a map view, we see that these four major stripes, in fact, we call them tiger stripes just for fun, are part of an intensely deformed region with a margin that abuts cratered or older terrain on the surface of Enceladus. Okay, this is the site of activity on this satellite. There are other regions that are semi-active or have been active in the past. But all of the real action today is happening right here. Here's a close-up. So these are the tiger stripes. They're sort of, if you like, rifts or valleys or troughs in the surface of Enceladus, a few hundred meters deep, and I'll show some fabulous close-ups a little bit later on. But the entire thing is intensely deformed, this entire region. And for those of you who, in elementary planetary geology, one of the ways we determine the ages of surfaces is to count craters, because it's like a steady rain of debris from outer space. Even in the outer solar system, there's a steady rain of cometary-like bodies. And even if we don't know what the absolute rate is, when you can't see a single crater, you know it's young. Once the heat anomaly was discovered, of course, subsequent orbits where the trajectories were changed to again get closer and closer to try to get better and better, higher resolution, and more spectral information to determine really how much heat was coming out and what the real temperatures of the surface were. Because the magic numbers, of course, the melting temperature of water, 273 Kelvin. So here's a view of the tiger stripes. Here's a better view of the heat anomaly. That's just at one stage. Let's do this again. And when you get in closer and take even better images, in fact, the heat anomaly breaks down and follows the actual tiger stripes. So the heat is actually coming out of these fissures or cracks, or is associated with them in some way. Also on this picture are 8 yellow stars. By taking enough visible images, the imaging team was able to triangulate where those jets were coming from. They're actually discrete sources. There's kind of a background, but there's also discrete sources. There are 8 major sources for 4 stripes. And the best data we have, just published just recently in the Journal of Geophysical Research by John Spencer and Carly Howitt and their collaborators, looks like this. So in fact, if you can sort of see on these images, the tiger stripes go right down the center. These various blocks are different viewing geometries for the different parts of the composite infrared spectrometer instrument, as well as some very high resolution stuff. And these stripes are warm. Some parts are hotter than others. And with this level of detail, you can add up all the thermal energy. And you have to do the modeling appropriately, because there's background and there's stuff that's not so hot and stuff that is hot. And when you put it all together, you get a lot of radiant energy coming out in the thermal infrared. In fact, our old numbers back from 2006 kind of looked like this. We just had data over here, but now we have data that goes all the way up to where the thermal peak is. So we can kind of tell really what the hottest stuff is. So these are the answers. We get a total heat flow. Well, this is in gigawatts. Okay, now 15.8 gigawatts will not mean anything to anybody, I think, in this audience. But if you spread this energy out over the south polar terrain, just divide it, you get a heat flow of 225 milliwatts per meter squared. And maybe that number doesn't mean anything to you. But the average heat flow of our Earth, our own planet, is 90 milliwatts per meter squared. So this little zone of this little icy satellite is putting out more average energy than the entire Earth per square meter. It's, for an icy body, quite warm. And the spectra of the hottest portions that the Sears team can analyze give them peak temperatures around, but not really exceeding, 200 Kelvin. Now that's not the melting temperature of water, which is 273.15 at 1 bar. But one of the things we know about the outer solar system is that you can mix stuff with water, and the water will melt more easily. You know how salt, or at least in the Midwest, we use salt to keep the roads clear down to a certain temperature. But if you really want to keep the roads clear, you want to use ammonia. Luckily, we don't do that in St. Louis. But you will lower the temperature, the melting temperature. The lowest melting point is what this magic word eutectic means, to 176 Kelvin. So we know that the inside of Enceladus at this place is hotter than the temperature that's necessary to melt water and ammonia together. Now the question is there ammonia? And I will show you that there is ammonia in a minute. Let me just back up a tiny bit and say, given that the body is made of rock and ice. It has a density about 60% greater than that of water ice. So we know there's a fair bit of rock inside. Given that this amount of heat is coming out of it, geophysicists like to say, well, it's probably separated. It's probably organized itself into layers the way the Earth has. You know, we have a metal core and a rock mantle and a lighter rock crust. We think Enceladus is structurally something like this. It's a modest-sized body, but it probably has a rock core and an ice mantle. And once you begin to think about ice mantle and rock core and a lot of heat, bells or light bulbs should go off in your head. You say, well, maybe is it warm enough on the inside to actually have water? And of course, water is denser than ice, so it wouldn't be on the surface. It would be underground, like in the Arctic or the Antarctic. So, ocean, question mark. So this is one of the big questions, one of the things that we talked a lot about in the last couple of days, about whether there's an ocean on Enceladus. And we probably think there is. Where does all this heat really come from? Well, I'll just give you a hint right away, and I'm going to come back to this. Even though this is a small body and by all means should simply be cold and dead, it isn't. And the heat comes from a gravitational resonance with another Saturn moon called Dione. Every 2 times that Enceladus goes around Saturn, it gets bumped by Dione gravitationally, and this pumps up the eccentricity or out of roundness of its orbit. But as it gets more out of round, you get tides, and they flex the body, and it's simple mechanical dissipation, like bending a paperclip back and forth, and it gets hot. But I'll talk more about this later. As I say, we could identify where these plumes or jets come from, and this is a montage of where we actually see some of these major plumes. And Carolyn Porco, the leader of the imaging team, on Monday gave an update on her triangulation with her people, and she now has more than 65 individual jets coming out of the South Pole from the Tiger Stripes and their branches, although there are still 8 major ones. Here's another picture, a cartoon of the Tiger Stripes and those 8 major plumes. You'll see they've been named after cities of the Middle East. This arrow indicates one path of the Cassini spacecraft through these plumes. Once we knew where they were, basically it was time to take the joyride, okay, through the plumes to sample them directly and measure their chemical composition. Here's just one indicator. It's like as you fly from time from closest approach, you basically can measure, let's say, the water density. That's what the plumes are mostly made of, water. That's what the stuff on the surface is, mostly water. And it basically shoots right up, and you see individual peaks that indicate when you're passing through a plume. And I'll just say that the ultraviolet spectrometer, when you do that stellar occultation I talked about, you can actually measure how much stuff is there. And the indication is that Enceladus is blowing out into space on the order of 200 kilograms a second of water vapor. It's trying to slim down, I guess. But the fun is, yes? Question?
No, I was just saying it's just all water weight, though.
Yeah.
Trying to slim down.
Yes, yes. Well, you know, for an IC satellite, though, that counts. But the more interesting stuff is to measure the chemical composition of the stuff that isn't water. So we have an ion and neutral mass spectrometer. That is something that can unscramble. It measures literally, because you're flying through the stuff so fast, the individual molecules break up and ionize, and then you can use a magnetic field to collect them, and you can at least separate them by charge to mass. And it's kind of a deconvolution problem, because even a simple molecule like water will break into hydrogen, it'll break into H2, it'll break into oxygen, it'll break into OH, it'll break into O and deuterium. And so you have a set of different molecular possibilities, but you do a bunch of experiments in the lab to calibrate your instrument. You're looking at simple compounds, and when you get a signal like this by atomic mass, which is what we mean, one would be hydrogen, then you put together your best model. And I've been lucky to work with this team to try to understand what these compositions mean. So here's a graph that shows various passes by Enceladus. Here's a stretched contour of the South Pole plumes. These are all different Enceladus encounters. There are various close encounter distances, and these are their tracks. The best track is this one here, this blue or purple track that goes sort of almost down the axis of the plume. And so it has the highest signal to noise. It's where we got most of the chemical information, And we published this in 2009. And this is what the deconvolved interpretation of this INMS signal is. There's a lot of water. It's about 90% water, but there's all this other stuff in it. A lot of high molecular weight stuff, organic stuff. So there's all sorts of weird organic material coming out of Enceladus. The most important other volatile actually turns out to be carbon dioxide. It's these red peaks. We see methane. We see ammonia. And we even see argon-40, the radioactive decay product of potassium-40. So it's a fabulous data set. Let me show you this in a little greater detail in this big old table here. I won't read all these numbers. If there's about 90% water, here's a mixing ratio of 0.9, there's about 5% CO2. So the most important volatile that's spewing out with the water is carbon dioxide. So if there's a water source for this stuff, and I'll try to argue that there is, it's carbonated, okay? It's fizzy water. But there's also a little bit of methane at the 1% level, and a little at the 1% level, there is ammonia. And we see this consistently from encounter to encounter. We also got, because of this, the fabulous signal to noise of this one encounter, a signal of argon-40, which is also very interesting because it doesn't start out as a gas. It starts out as potassium-40, which is in the rock. And so to get this out means that there probably had to have been some sort of water-rock interaction to actually reach the potassium, because that's actually what will happen. Let me just remind you that ammonia is very important, because here is a close-up picture of some of the tiger stripe regions. That's one of the tiger stripes, Damascus sulcus as we call it. This is the position of two of the individual vents. And these are some individual temperatures right down sort of the valley, okay, on the order of the melting temperature of water and ammonia together. And we see the evidence for ammonia in the plumes. So we think there must be liquid down in there somewhere.
What is the eutectic composition?
About 30%, 33% ammonia. That's right. We're not looking at a eutectic spray, but as long as the ammonia is there, you'll never freeze it all unless you get colder. The argon is a very interesting number. I don't have much time to talk about it. It's really the difference between the counts we get in the mass spectrometer, that are these black curves here, and the best fit model for every species in the analysis. And basically, Brian McGee and Hunter Waite could not close this gap. And so we have this signal that we ascribe to argon-40, which is very interesting because we know how much argon-40 is likely to be produced inside Enceladus over all of geologic time. And if this is a true measurement, it means that the rate we're spewing argon-40 into space means that we'll deplete Enceladus's reservoir of argon-40 in only, let's say, on the order of 10 to 100 million years, which either the measurement is wrong, or it means that we're looking at Enceladus in a special time, or it only operates like this periodically. That is, this is an estimate of the duty cycle of less than 1% for the whole age of the solar system. Unfortunately, we haven't been able to see this argon-40 again because the signal to noise of the other encounters through the plume are just not high enough. So we'll just have to leave that where it is. Let me show you. Here's a theoretical model by Misha Zolotov at the Arizona ASU. And basically what this is a complicated chemical analysis of given water and rock interacting. It's the kind of thing sedimentary geologists do. They ask, if you have a kind of plausible composition for outer solar system rock, what kind of stuff will get dissolved in the water? And what you see, the stuff at the top is what's important. Well, it's just like the Earth's ocean. You get chlorine, you get sodium, you get some potassium, and for the given chemical environment that's in the model, you actually get carbonate and bicarbonate. And it turns out that another machine that goes through the plume measures the composition of the hard particles, the actual particles we see in those visible images. And these particles break up, and they see that most of the icy grains they fly through are somewhat salty. They see sodium chloride, they see sodium carbonate, they see sodium bicarbonate, they even see some calcium chloride. Potassium chloride. So it's salt water, except it's only slightly salty. In fact, the salinity of this model in grams per kilogram of H2O is about 1/10 of that of the Earth's seawater. But this is the general idea. We actually think that all of this stuff together, the CO2, which of course obviously can dissolve in water, the argon-40, which could be leached, or at least the potassium can be leached, and in fact, the fact that the particles have, about 1% salt in them to most people is a high indicator that there really is water down below. Now, this, of course, is a cartoon. It's not a model here, but that's kind of where things are heading. Well, here's some of the data from the cosmic dust analyzer. And so these are the peaks, in atomic masses. And so these are the things that they see. They see sodium. They see sodium chloride and various complexes. There's the carbonate. So, and it makes sense. Carbonate and carbon dioxide in the gas. It all fits together. Sodium chloride, carbonate, bicarbonate. In fact, what we talked about at this workshop, in fact, that almost all of the particles in the lower part of the plumes are salty. They're all contaminated with salt. And the only way that people have proposed different kinds of scenarios for how you could get particles and gas out of Enceladus, 4 of these little models here involve water of some sort, and one doesn't involve any water. It's just sort of vaporizing hot ice. But that one doesn't work very well. And all of the information we have says that this is probably not going on. And in fact, the people who work most on the salt particles, and in fact the vapor, which is coming out at a rather high velocity, about 1 kilometer a second, like this one. And whether this is ultimately the right answer, I don't know, but there's basically pockets of slightly saline water down below, maybe under some gas pressure because of effervescing CO2, and the stuff shoots up these vents to the surface. Remember, though, it's a relatively low-gravity body, so you could actually have a deep source, and in fact, the pressures would not be extraordinary from any kind of terrestrial perspective. What a wild world. What a crazy place. Do all icy satellites behave this way? Well, many of you probably realize the answer is no. Enceladus is in a very special position. And what's interesting is that the next moon closer to Saturn, little Mimas here, isn't like this at all. Mimas is just a little bit smaller. It definitely has less rock in it. Its density is only a little bit more than that of water ice. And you can see at this picture against the limit of Saturn that it's very heavily covered in impact craters. It's still lovely. It has a very nice round or ovular shape. It's kind of like an egg. Okay, so it's kind of relaxed into some sort of equilibrium configuration. We get closer and closer with Cassini. The rings are in the background here. If you love craters, this is a great place to go. If you're looking for cryovolcanism, though, you're probably out of luck. It has one great crater, which of course is very spectacular in a sort of, relative sense, although it's really only 130 or 140 kilometers wide, less than 100 miles wide. But it dominates the figure of the body, and it's named after the discoverer of the satellite, William Herschel, the same man who discovered Uranus. There's some fabulous pictures of Herschel depending on the geometry. Okay, and this has inspired some various interesting ideas as to what is the true nature of Mimas and Herschel. It's nice to know that when Darth Vader retired, he took up something useful as a hobby. Okay. This is a map put together by Paul Schenck, which he showed at the end of last year at the American Geophysical Union meeting. And you can see the entire surface, as Cassini has seen Mimas, is just covered with craters of all sizes. And there's Herschel, which dominates one hemisphere. We can look at the topography of Mimas. And again, you can see the craters very distinctly, okay, where dark is deep. And here's the fun part. If you compare, this is something Paul put together, Mimas and Enceladus, surface area appropriately projected to the same vertical scale from plus to where black is -5 and white is pure white is +5, a total elevation range of 10 kilometers, you see that Mimas, even though it's nicely shaped like an egg, is on smaller scales very, very irregular because of all those craters, and Enceladus is way smooth. You can actually see the craters if you look closely up here, those of you in the front, but basically with some larger regional undulations, it is a pretty even body. And that's because it's so much warmer that the ice has relaxed glacier style. This has led, though, to some head scratching among planetary dynamicists, perhaps unnecessarily so. But so this is where the question is, why can't Mimas be more like Enceladus comes up? The energy that comes into a tidally heated satellite can be simply described by an equation. There's some numbers. There's the gravitational constant. There's the mass of the planet, which in this case is Saturn. There's the radius of the satellite in question. We know these things. There's the mean motion, or how fast the satellite's going around the planet. There's its orbital eccentricity to the square power, the distance from Saturn to the sixth power, and then a couple of mystery factors that have to do with how deformable the body is. That's the K2, or the love number, potential love number, and Q, which, for those of you who remember your physics, is the dissipation factor, or the quality factor, where a very high or infinite Q means no dissipation, and a low Q means a lot of dissipation. So if this is a low number, this is a high number, so you get a lot of energy. It was pointed out because the eccentricity of Mimas, its orbital eccentricity that is 2%, which is big. The eccentricity of Enceladus is less than 0.5%, so it's much smaller, factor 4 smaller, really factor of 5 smaller. And so there was a well-known paper, now almost 30 years old. You may recognize Steve Squires. He's the PI of the MER rovers. It should be noted that for the same value of the specific dissipation factor Q, Mimas should currently be tidally heated at a rate at least twice that of Enceladus, if Mimas's rigidity is like that of rock, and as much as 30 times if its rigidity is the same as Enceladus. That is, if its K2 over Q is the same. It's just a question, you put in all the factors about the mass and the mean motion and the distance from Saturn, but as long as the eccentricity is so much bigger for Mimas, you're going to get 30 times the energy. Yet Mimas shows no evidence of recent tectonic or any other activity, and this has become known as the Mimas Paradox, or the Mimas test. Somehow people are just not quite figuring out what's going on. Now, maybe this is a little overblown, but it's a fun thing to talk about because it illustrates interesting things about satellite motion. Well, here's the key to the Mimas paradox, or how Mimas passes the Mimas test. This resonance I talked about, this idea that Enceladus is locked into a motion with Dione. It's the same kind of resonance, actually, that powers the volcanoes of Io around Jupiter, because Io is locked into a resonance with Europa and with Ganymede. It's also what keeps Europa warm and maintains its ocean, which is another icy ocean world. But anyway, 2 trips around its orbit for Enceladus, it comes back to where Dione is. Well, actually, it almost comes back to exactly where it is in inertial space. It turns out that Enceladus's orbit is out around, and what happens is that in that time, the orbit precesses forward, that its orientation, this is driven by the oblateness of Saturn. So they actually meet, when Enceladus meets Dione, they meet again right at the point where the closest point of Enceladus's orbit is to Saturn. And when that happens, and that's what repeats. So this is an eccentricity type resonance. Every time the satellite Dione, which is much bigger, meets Enceladus, it gives it a kick right at its closest position to Saturn, and this pumps its orbit up. It sends it more out around. This is what maintains its eccentricity. And eccentricity tries to damp down and dissipate energy, but it keeps getting pumped up by Dione. It's effectively an infinite reservoir. Where does the energy really come from? It comes from the rotation of Saturn, and you're never going to run out of that. Now, people think that Mimas is also in a mean motion resonance with Tethys. Tethys is the moon between Mimas and Enceladus. I mean, it's outside. It's the one just right next to Enceladus on the outside. But it turns out that this kind of mean motion resonance doesn't involve the eccentricity. It involves the inclinations of both moons. And so here's their orbits again. If you can imagine their orbits tilted a little bit with respect to the plane of the rings of Saturn, Mimas will go around twice and meet Tethys again, and they're not meeting at periaps, at the closest point of Mimas's orbit. They're meeting halfway in between the what are so-called nodal lines where the individual orbits of Mimas and Tethys are precessing. So they keep bumping up at this point. This doesn't excite the inclination. It doesn't really do anything. It excites the eccentricity in one little bit, but the orbit you keep meeting it. Tethys keeps meeting Mimas in the sort of uniform parade of positions all around its orbit. So it's trying to pump up the eccentricity from all different directions, and so it doesn't add up. You don't change the shape of the orbit. It doesn't excite the eccentricity. There's no ultimate source of eccentricity for Mimas. The fact that Mimas has an eccentricity means that it's some sort of fossil. It's just a leftover of some other process. This is the key, and so I'm going to repeat this because this is, why can't Mimas be like Enceladus? Conjunctions in the Enceladus-Dione resonance occur at Enceladus periaps, and perturbations act to raise Enceladus's eccentricity. Tidal dissipation or heating within Enceladus acts to damp the eccentricity, but it's a renewable resource, which is what, of course, we all need. Conjunctions in the Mimas-Tethys resonance circulate with respect to Mimas's periaps, so its eccentricity is not excited. In fact, it's completely asleep. Its eccentricity is not a renewable resource and is being secularly damped. That is, it is actually slowly decreasing, but at its own slow rate, albeit slowly, due to Mimas's cold state. It's a cold, inert body, and it doesn't have much of an eccentricity. I mean, it's basically not getting heated. You can ask, well, what happens if that eccentricity, that 2%, actually does damp? What happens if it does collapse? Well, you get a one-time energy input. It's like draining your battery without a recharge. And you can calculate the maximum temperature you'll get out of this, and it's just a delta of 60 Kelvin. And that's the maximum. That's provided you can keep all the heat in. In reality, it will conduct to the outside and radiate to space. And so it's a small body, and so if it releases energy slowly enough, you'll hardly get any effect at all. So Mimas is just cold and inert, and its eccentricity is just hanging around. We can justify its cold and inert state by saying, well, let's calculate as a function of its internal temperature what its own dissipation factor should be. And so as a function of the internal temperature from 100 to almost, let's say, the melting temperature of water, ice, mostly your Qs are this is a log scale, orders of magnitude greater than a Q for Mimas of 1,000. So you're just not going to get any dissipation unless you get very warm. And even if you were warm, then you just dissipate you get your 60 Kelvin, and then you'd be dead. That would be it. Where does this eccentricity come from? Mimas's eccentricity, as I said, is about 2%. Well, maybe it's some sort of primordial thing that happened to do with the formation of the satellite or the formation of its resonance with Tethys. And it's just been hanging around. You can even, as we always do in planetary science, when you can't solve anything, you jump up and say, giant impact. It works. No, really. It's a choice of last resort, but I can show you that it fails. The best answer, probably, is that Mimas passed through a resonance with a different satellite in its past, and its eccentricity got pumped up, and has in fact been falling since then. And I'll show you a calculation of that. And there are more obscure notions, but I won't really address those today. To actually give Mimas's eccentricity, that 2% eccentricity, in one big whack, you would need an impactor under the best possible circumstances that was 60 kilometers wide. That would blow up the satellite, so that's why we say it won't work. If you run the clock backwards, starting with today at time equals 0, the satellites evolve because Saturn is spinning, and the tides that the satellites raise in Saturn actually push the satellites out. Just like the tides that the Earth's moon raises in the Earth are pushing the moon out at about 3.5 centimeters a year, which we measure with mirrors and laser beams. The same thing happens to Saturn. We don't really know how fast it happens, but it might happen this fast that this would be the synchronous orbital position above Saturn's atmosphere. This would be Mimas's position in the past. And in a relative sense, here would be Enceladus's position. You can imagine at some time in the past, it actually passed through a resonance with Enceladus, not with Tethys. But anyway, you can do these sorts of calculations. They're sophisticated. They've been published by Jennifer Meyer and Jack Wisdom at MIT. And this is just the evolution of the eccentricity of Mimas as it encounters the Mimas Enceladus 3 to 2 E Mimas resonance. That is, it pumps up the eccentricity of Mimas. And this shows this happening at 2 billion years ago, and the eccentricity goes from basically a very small number up to 5%. And then it slowly damps away. And then here is a different possibility, a different resonance in the past. This is probably the answer. In fact, Mimas has probably had a higher eccentricity, and it's been slowly decaying, and it gets a little bit of extra heat, but not very much, but maybe enough to help it become nice and round. Not enough to drive volcanoes, though. So here it is. Here's our friend Mimas. It's had some fun, but not too much. Is the story over? Well, no, you know, let's do due diligence. Let's at least look. Does Mimas pass, instead of, you know, casting a dark shadow over the dynamics of the Saturn system, Mimas passes the Mimas test. But there's still mysteries at Mimas. Just as that infrared mapper could detect the hot spot at Enceladus, for doing due diligence, you can turn it on Mimas. You don't maybe expect to see a hot spot, but you kind of expect to see normal stuff. You expect to see, here are expected temperatures. You expect to see temperatures that go from, the scale here is from 74 to 96 Kelvin. You basically, this is noon on the equator of Mimas. So you just basically expect afternoon temperatures on Mimas to be warmer than nighttime temperatures. But of course, what happens when you make the measurements is you get this pattern, the Pac-Man anomaly. Okay. Somehow, daytime on this part of Mimas, the surface is anomalously cool, and this is what the visible image that corresponds would be here. Maybe the simplest thing to say is, oh look, well there's Herschel, the big crater. Maybe its ejecta has something to do with it. It's changing the thermophysical properties of the surface. But that's actually not the answer. Here's a map, a color map of Mimas, and you can kind of see that one side of it, where Herschel is a little bit bluer, and one side is a little bit redder in a sort of relative sense. And Paul Schenk and I, with some other people, we worked on a paper which came out just earlier this year, looking at these sort of color patterns on all of the satellites. And what you actually see when you do a global ultraviolet, infrared to ultraviolet color ratio map is that Mimas, you can still see the crater in here, kind of has this pattern where it's kind of brighter in the infrared on one part and darker in the infrared on the other part. It actually turns out to be brighter in the ultraviolet is what it's really sort of bluer, that's where the difference is. But it's actually an ovular pattern. It's not really just centered on Herschel. This brightening actually corresponds to where we expect E-ring particles from Enceladus to be bombarding Mimas and freshening and frosting it. Sort of like flocking it at Christmas time. Here's the image. Again, now not the visible image, but the color ratio image, and there's a very nice correspondence between this blue or ultraviolet anomaly and the Pac-Man thermal anomaly. It just means that things are not getting as warm as fast as they should be for fluffy ice particles. And in our paper, what we show is that the charged particles that are circulating around Saturn, the highest energy particles are gyro-rotating on such long arcs that they're effectively moving backwards with respect to Mimas's orbit, and they're actually striking this hemisphere, what's called the leading hemisphere of this tidally locked satellite. And this is a calculation by Chris Peronicus at the Applied Physics Lab in terms of some appropriate units of energy, and it really is a very nice match to this ultraviolet pattern, and it's also a nice match to the thermal anomaly, the Pac-Man anomaly. What must be happening is that these electrons are drilling into the ice and depositing energy that's below the depth that the visible light is sensitive to. It's changing the way the ice particles are contacting each other. They're making them, they're kind of sintering them, or making them, gluing them together in a way so that they transmit and release heat more slowly. So things stay a little bit cooler in the daytime. And we see a similar anomaly, less intense on Tethys, and so this is what we think is going on. This is not an endogenic problem. This is not stuff spewing out of Mimas. This is stuff from, on one side of Mimas, it's actually coming from Enceladus, and on the other side, these are charged particles in the Saturn magnetosphere, like the sort of Van Allen belts of Saturn. Well, let's finish up by looking back at Enceladus and looking at its color pattern. So this is the same stuff for Enceladus, and you'll notice that here's the south polar terrain here down at the bottom. This is a cylindrical projection. It's again, it's a there's an infrared and ultraviolet component. So you see this sort of blue, extra blue along the tiger stripes. But you also see that things are kind of bluer up to kind of pathways towards the equator and beyond. We can contour that down here. This is something that Paul Schenk showed at the recent workshop we had. And so these are the contours of blueness, if you like, on Enceladus now. Back to Enceladus. Up here is a completely separate calculation by a German group led by Ralph Jomann of where the icy particles from the plumes land. This is the ice coating on Enceladus. This is a completely independent prediction. And there's, for science anyway, this is a pretty good match. So the color patterns on Enceladus aren't being controlled by, let's say, the magnetosphere. They're, of course, being controlled by the plumes themselves. And of course, if these particles are controlling the albedo or reflectivity, they may also affect the surface morphology. In fact, this is part of that model that was presented. And this is the deposition rate. Now the ratio has been inverted, so now this is dark. So this is basically extra blue or extra ultraviolet. But these are contours of plume deposition in millimeters per year, and this is like 10 to the minus 5. So in about 1 million years, you'll get about a centimeter of stuff falling. But that's far away from up here. Down here, you'll get more. If we look down at the area of the tiger stripes, we can look close to them, and you actually will see, here's the inside, looking down the valley of a tiger stripe. When you look down at them, you don't see the plumes because it's so tenuous that the reflectivity from the surface swamps everything. But this isn't just fuzziness because it's sharper up here. This is actually plume fallout, burying the terrain. And in fact, Paul in his presentation tried to find some really nice places. Here's a piece of Enceladus terrain. There's a 10-kilometer scale bar that's really at the edge of the whole south polar terrain, which is down here in the basement. And now here's a crater, so we're moving up into the crater terrain. Right at the edge here, let's look at this box. He gave me this picture, and this may remind you of basically a snowy terrain on Earth. And so we had a lot of discussion about snow on Enceladus, except of course there's no atmosphere and we don't have snowflakes, but we have these little fine sort of toner-sized particles of ice burying. This is a surface that's been fractured, but it's not anywhere near as active as those south polar terrains. So this stuff looks blanketed by this fine mist of ice smoke. Of course, lots of stuff near the tiger stripes is so active, it's so geologically rapidly deforming that it doesn't get a chance to be buried. And so I'm just showing you have to be careful because like here, this piece here, this is just lower resolution. But better resolution here near Baghdad Sulcus, you can see just how the level of detail in the terrain is, and it's deformed everywhere. It almost looks like a rug that's been compressed. You have sort of like ups and downs. Folds and valleys was what we think is going on. This, by the way, is just one of the spots of one of the plumes, major plumes. Here's a nice close-up of the terrain that's right near the tiger stripes. Intensely deformed ice surface. There's no craters anywhere. You don't even see much in terms of fine particles. You can actually see lots of boulders. These are like...
What's the width of that image?
These individual bits are on the order of 10 kilometers.
No, 10 meters, you mean.
10 meters, yes. Let's go back and I'll show you. So let's see. So this thing would be about 2 kilometers. So we're looking at things that are on a scale of 1 kilometer, let's say, this way. This is amongst the highest resolution stuff we have. It's all finely fractured, but this is an amazing, these images are simply amazing to us in the geological world. It's so amazing that Paul Helfenstein at the workshop we had just yesterday has proposed, he's proposed this in the past, but we haven't really seen all the details yet because it's not published. He believes that this is a piece of tiger stripe stuff, that there are all sorts of fractures and offsets, what are called strike slip or transform offsets depending on the orientation. And he's tried to make an analogy between the spreading tectonics on the Earth's seafloor, which is over here, the East Pacific Rise in the Pacific Ocean, and over here, and Enceladus, where he basically sees similar structures of spreading for two different, I can't quite read the scale. So this is like 10, no, I just don't see it. It's like 1, that's 5, I think that's a 4 kilometer scale bar, but I'm not absolutely sure. If this is true, it's really quite fantastic that we actually have active spreading on an icy satellite. Now, it's not exactly like the plate tectonics on the Earth, because on the Earth, the plates are rather strong, and they basically ride, once they're formed, at the spreading centers out to the subduction zones, you know, like near Japan, where the recent earthquake was. On Enceladus, the surface is intensely deformed, probably because the ice is, in fact, failing in a sort of semi-brittle manner at the surface under compression. This has led to a general idea about what we think is really going on there. And I could go farther into this, but I'm really out of time. And this comes from a theoretical paper of Gabriel Tobey et al., in which the idea is that there is a core, there's an ice shell, but there is a regional ocean in the southern part of the satellite. Because it's decoupled from the shell, the tidal flexing that Enceladus undergoes is quite strong, and you get a lot of heat being pumped into this part of the ice shell. When you pump enough heat into the ice shell, you get convection. That's what these arrows are. And then that can lead to the ripping apart and all the distortion at the surface. It's so much tidal heat that the ice is probably being raised to the melting point. And since it's, in a sense, ice lava is denser than ice, that is water denser than ice, it goes down. And so we have thickening at the base of the ice shell. And then because of isostasy, just like with icebergs, the surface subsides. And we actually have evidence for this surface subsidence when we look at the topography of Enceladus as seen in stereo. Here's the south polar terrain. It's a vast, sort of flatter, lower lying area. I'll show you this in a little bit closer detail. We blow this up. Here's the south polar terrain. There's a difference in resolution of the images that we have. But here are topographic profiles going, and with respect to the mean elevation of Enceladus, the whole south polar terrain is sort of uniformly flat except for the individual tiger stripes at about 500 meters, which probably means that the shell is about 10 kilometers, 5 to 10 kilometers thinner down below. If you take this spreading analogy all the way and use standard geophysics, you get some rather amazing ideas or concepts. You can take that regional heat flux that I told you about, spread it over the entire south polar terrain. There's an equation for the release of heat in seafloor spreading. And if you do that, assuming each tiger stripe is a spreading center, and they're basically, it's like an accordion moving out. If you just do that, you can then estimate how fast the actual spreading has to be occurring. Where the ice down below is, let's say, at around the melting point of water, and the ice at the surface at the South Pole without any heat is very cold. And you get that the spreading rate, the half spreading rate, if you like, is 25 centimeters a year. This is big. Okay? It's actually bigger than the Earth by about an order of magnitude, which would mean that the entire age of the structure we're looking at, the present structure without the craters, the whole South Polar terrain, is less than 1 million years, maybe only a couple of 100,000 years. It's a fantastic concept. We don't really know if it's true, but there are indications that something like this might be going on, deforming the South Pole. So, just to conclude, this is one of the movies that Paul Schenk has put together, looking over one of the tiger stripes and the ropey terrain that it's sort of either created by compression or by spreading and compression nearby. What we see at Enceladus is, it's the key, I believe, the key to understanding all of the activity on the icy satellites in the solar system, because there are moons that were active in the geologic past, but it might be billions of years ago. There are moons that might be active today. Neptune's Triton is an example in Europa. But at least in Europa's case, we're not sure, even some of the things that we look at that we're very familiar with have not been clearly active in the historical past. They were active maybe 1 million years ago or 10 million years ago. But this satellite is doing its thing right now. And we have the tools and the kind of instrumentation to continue to study it, and may unlock the secret to how all icy satellites evolve. And
before you leave that movie, how high is the ridge, the height of the ridge?
A few hundred meters.
Okay.
Okay, I could show you if we go all the way back to the. So this is, if we go across here, just take one of these tracks, you can see these sort of bumps. So this is 500 meters. So individual tiger stripes are on the order of 100 to 200 meters.
How do we find the clip on Google?
What you want to do is search on this. In this case, this is in a paper. The movie that Paul Schenck has a bunch of movies on his website at the Lunar and Planetary Lab. If you just Google SCHENK LPL, you'll find his homepage. LPI. Thank you.
It's not USRI.
Well, I mean, when you Google it, his stuff will come up. And so he has all sorts of crazy stuff. I just wanted to say that, of course, the party is not over at Enceladus. The Cassini mission is proceeded in 3 phases, and we're basically moving, we are now into the 3rd and final phase of the Cassini mission and the extended Cassini mission. And what you see here are the number of orbits in each sort of fiscal year. This is sort of NASA stuff, and encounters with various moons. So we have Titan, the big moon, but we also have Enceladus encounters as a special case. And so we're going to have a bunch of more encounters coming up with Enceladus, and then a gap, and then some final Enceladus encounters in around 2015 before the end of the Cassini mission, which will be a different and spectacular thing because it will be dropping the orbit inside the ring system. Okay, and so that's the story of why Mimas can't be like Enceladus. Mimas passes the Mimas test. The real question for planetary science is, how does Enceladus pass the Enceladus test? That's okay. Thank you very much.
Okay, we probably have time for a couple of questions.
Sir. Oh, that's right.
It's fascinating. Thank you so much for that. You talked about lifetimes and how old these features are and all. One thing I didn't hear is anything related to the fact that water, even at ice, even at 50 to 90 K, has a vapor pressure. So what are the lifetimes from that sense?
When it's that cold, the vapor pressure falls so fast that it's stable indefinitely. Just like the rings of Saturn aren't sublimating away. Yeah. Now, if things were at 180 or 250 K, they would, but they cool off to space. And in particular, the South Pole is, without heat from the ground, from below, is very, very chilly because it's still the pole. We're talking 50 Kelvin. Other things like ammonia probably do get lost. So we can see ammonia. I didn't mention it in detail, but the infrared spectra of the rest of the surface shows water ice. We also see CO2, so the carbon dioxide is on the surface, but we don't see ammonia on the surface. We think that stuff is too volatile and gets lost. Yes?
Hi, great talk. I wasn't clear on the 25 centimeters a year of spreading. Is that over the entire South Pole region or at each geyser?
Each one of those 4 things, like an accordion, each one.
Each one, okay. Yeah. Thank you.
If you want to account to bring up the hot ice and expose it and account for that heat. So it's an energy argument about how fast you have to bring the ice up and cool it off.
So in that last warm ice in the South Pole with a regional ocean model, does that model have cold ice touching directly the rocky core of the rest of the moon? And how deep would that ocean and how big would that ocean be?
Yes. That was a specific paper that looked at the question is, could you still get enough heat to run things if the rest of the ice was stuck? And so that's how basically the ocean has to be almost a hemisphere wide, but it doesn't have to be a global ocean to work that way. It also helps if we only have a regional ocean in terms of the long-term energy balance of the whole system, which is another whole argument. The ice, the layer could be thin, but it's probably at least on the order of 15 kilometers. And the reason is that we have another line of evidence that the rock core is itself irregular, and it's a little bit depressed at the poles. So you can get what you need that way. Yes, sir. Let's
She's got the microphone.
Oh, I'm sorry. Who has? I'm sorry. Oh, hi, Mary.
Hi. In one of your temperature maps near the beginning, it seemed like there were actually some pretty hot spots equatorially on Enceladus.
I think that was all noise.
Oh,
that
okay.
very first map, that was the lowest signal to noise.
Okay. Okay.
No, but in fact, the best thing to do is to look at the paper by Hewitt and Spencer in Icarus, which talks about the overall thermal inertial models for all the icy satellites, where they don't deal with the South Pole of Enceladus, they deal with the rest of it.
For the next 18 months, as Cassini goes by Enceladus again, what are the 2 or 3 big things you're looking to sort out or solve or understand?
Oh, well, I would, right now, the seasons are working on Saturn such that the South Pole is slipping into darkness, sort of, and so that may, in fact, improve the heat flow measurements because you won't have any background to subtract. It'll get really cold because the polar night on Saturn lasts, what, 13 and a half years? Yeah, it's a long time. So that'll be good. There's always a chance that we'll fly, looking for more data on plume composition. Okay, I'd like to see if there really is argon-40 in the thing. Plus, you know, now that people know what they're looking at, they're kind of tweaking things. There's also a very important measurement which has not been fully analyzed, and that is some of these passes, they don't actually use the instruments. They just try to track the spacecraft as accurately as possible to get gravity. And the sort of perturbations of the gravity will actually tell you what the subsurface structure is like, or at least constrain it. So like this model is testable. This business with the regional ocean is testable with gravity data. So there's at least one more gravity pass to put together into the hopper. So that's one thing that I can't tell you about yet because we don't even have a preliminary answer.
Okay, if you've got any further questions, I'll encourage you to come up and speak to Bill after the talk. Bill, we have a antique SETI mug as a memento of your fabulous talk here today. So if you'll join me.
A second coffee mug from my house.
Right, exactly. This is special. Please join me in thanking Bill.
All right.